Okay, what I want to talk about is equipotential surfaces, or equipotential surfaces. So this is kind of analogous to electric field lines. So let's say we have a positive charge. Because the voltage is equal to Coulomb's constant times the value of the charge divided by radius, if we draw circles around this positive charge, each one of these is going to have a different voltage at equal distances. So these are lines at equal potential. The electric field lines were lines which went in the direction the electric field went. Okay, so what else can we say about this? So let's say there's a voltage of 10, this is a voltage of 20, this is a voltage of 30. Actually, it goes the other way around. It's greater as we get closer. So this might be 10, and this might be 20. This might be 30. Right now I've got them equally spaced, so that would make sense. So at any fixed radius, with these being fixed, you get a fixed value voltage. Okay. Now, in reality, what happens is it looks more like this. That was probably an incorrect drawing. So what you'll get in reality, if you draw lines that are the same distance apart, you'll get closer lines. Oops, let me do that. Closer lines when you're close to the charge. And as you go away, they get further apart. So the difference, the distance between the two, the circles, gives you an idea of the rate of change of the voltage with respect to the distance. So this is saying the voltage is increasing more rapidly here than it is further away. So these actually should be even bigger. Probably should get away even farther like that. Okay, so they're spreading out. The interesting thing is if I wanted to look at the quantity dV dx, let's assume this is the x direction, and this is the y direction. dV dx is the distance, basically the distance between the lines. The closer they are, the higher this thing is. It's actually 1 over, I guess, the distance between the lines. Because as this distance gets closer, the rate of change is like looking at a mountain. If you have a constant elevation lines, you're going to, and they're close together, that means that you're in the steep area. If they're further apart, then it's a flatter area. So what's happening is that the change in electric field is, the change in voltage is greater, and therefore we said this was equal to the electric field. I think that actually is a minus sign here. In the same way, if you went in the y direction, in this case, dV dx is equal to dV dy because there's concentric circles, but that's not always the case. So then if you have multiple particles, let's say you have a particle here that's 2 micro coulombs charge, and then you have a -1 over here that's -4 microcoulombs, and you have another one here which is -2 microcoulombs. You could then have equipotential lines associated with these 3 points. They would be basically the summation of the individual ones. I don't know exactly how this thing looks. The interesting thing is that the voltage is going to be a positive around the positive charges, and it's going to be negative around the negative charges. At some point in here, in the middle, you're going to have the voltage is equal to 0, which is fine, because what's important is not the absolute value of voltage, it's how much the voltage difference is and how quickly that difference is. The absolute difference, delta V, is related to the change in potential energy, whereas how close they are together tells us something about the electric field in that region. And I will show a separate video with a simulation looking at these equipotential lines.
So, we're in chapter 16. We're talking about voltages, and one of the first elements of an electric circuit that we introduce is called a capacitor. And we've already actually shown this when we were introducing the whole concept of electrical potential energy. We had two conducting plates that were separated by a certain distance, delta x. No, actually, we didn't call it delta x, we just called it, we're going to call it d in our case. And really these are in 3 dimensions, so I could draw this back like this, and draw it back like that. So that's it's like a plate. And so back here would also be d, so they're equally spaced. And these are connected somewhere to some sort of battery, possibly. And so on the surface of this plate, we're going to have positive charges. And you don't just have a small number of positive charges. You have a huge amount of positive charges. So we're talking billions, trillions, bazillions. So we might have a battery that is going to take electrons, move them over here, and take them from the other side. And as we showed in the introduction of electrical potential energy, there's an electric field that goes between these two plates. And if the plates are close enough and the area is big enough, so if the separation distance is small compared to the areas of the dimensions of the capacitors, then we find out that, for one thing, that you can store energy in this. You can store charge. So the charge is associated with how many excess electrons we have over here and how many we take out, and it's always equal amount. So for every electron that comes out of here, we put 1 in there. And the value of a capacitor is defined by the amount of charge that can be held on the plates per the voltage that is applied to the plates. The potential difference applied to the plates. So Q is charge, and charge has units of coulombs. And really well, let's finish my thought here. And then you have voltage, which has units of volts. And the value of the capacitor the capacitance of a capacitor depends upon a number of things, which we'll talk about here in a second, but it's mostly the physical dimensions of the capacitor. So if you put 5 volts, say, you put a potential difference of 5 volts across the plate, and the capacitor is rated at some value, you can calculate the charge. You can just manipulate this to solve for charge. If you know capacitance and voltage, you can solve for charge, or you can solve for voltage if you know charge and capacitance. Now, typically, capacitors have values of capacitance which are fairly small. I mean, they're on the order of what we would call, well, before we get to there, let's define this unit of capacitance, which is coulombs per volt. So this is the capacitor, that's coulombs, and we call that a farad. So the value of a capacitor might be equal to 1.0 times 10 to the minus 6 farads. So it's not, you don't usually see capacitors with 1 farad. And you'll say, why did we choose such units so this thing is so small? We'll see why that is later. Okay, so a farad. And we would represent this as 1.0, and we'd use this mu sign to stand for micro. So it would be 1.0 microfarads. You could also have something like 5.4 millifarads. That's a fairly big capacitance. That would be 5.4 times 10 to the minus 3 farads. And there are things like picofarads. So let's see how we have 7 picofarads. Pico is 10 to the minus 12th. So those are the values for capacitors. Farads are the units. Typically they are fractions of a farad, fairly small fractions of a farad. So let's say I have a capacitor. Let's say I have a capacitor which has a capacitance of 440 microfarads, and I apply a voltage across that capacitor of 12 volts. What's the charge on each plate? So you'll have a negative charge on one plate, positive charge on the other plate. So the charge is going to be equal to, let's go back and see what we did here. So charge is equal to capacitance times voltage. So all we do is take 440 times 10 to the minus 6 farads multiplied by 12 volts. And what we will get, so 440 e to the minus 6 times 12, I get 0.00528, and the units for charge are coulombs. Then you might rewrite this as 5.28 milli, and it shouldn't be, it should be coulombs, millicoulombs. So 1, 2, 3, you get 5.28 millicoulombs. Okay, so that's what a capacitor does. We'll talk about the energy storage later. So we just introduced the idea of a parallel plate capacitor. Consists of 2 conductive plates with a space in between them in a certain area. And we said that it has a certain value capacitance. So what is that capacitance equal to? Well, you can derive it by looking at just the definition of capacitance, which is charge per change in voltage. And if you use, this is an application of, what's it called? Gauss's law. So what you find out is that the voltage across this parallel plate capacitor, because it has a constant electric field between the two, is just equal to the electric field times the distance between the plates. And the charge is just equal to sigma, which is the charge per unit what is it? Yeah, this is the charge per unit area times the area. So charge per unit area times area gives you the charge. And so then what you can do is you can divide both the electric field from, so the electric field, this is not actually from Gauss's law. This is just saying charge is charge per unit area times area. From Gauss's law would say that the electric field is equal to the charge per unit area divided by epsilon 0. And then we have the distance between the plates, and we have charge per unit area times area, and you see the charge per unit area drops out, and you end up, and this epsilon 0 then will come to the numerator, so you end up with epsilon 0, which is a constant, times A divided by D. So A is the area of the plate-to-plate area, and epsilon 0 is a constant, which is related to Coulomb's constant, and the value for epsilon 0 is, look in the book, it's 8.85, and it's called the permittivity of free space. and the units are coulomb squared per Newton meter squared. I'm looking at the back leaf of the book. And then D is the plate distance between the plates. So what is going to give, what you want is typically a large capacitance if you're trying to store energy. So how to make capacitance large, you have to make area large, or you have to make the distance small. Epsilon 0 is a constant, so those are the only things. Now, if all we relied upon was just an air or vacuum between the plates, we would get not very high capacitance values. And also, if we just had two plates that were trying to sit next to each other, it would be hard to get them to not touch each other because you'd have irregularities in the surface. So there are ways of increasing the capacitance, which we'll talk about, but that's the basic idea. So let's just put in some numbers. Let's say the area, let's say it's 10 centimeters by 10 centimeters, which is fairly big. 10 centimeters times 10 centimeters. We're going to divide by 100 squared to get into meters squared. It's 100 centimeters per meter. So you'll take 10 times 10 divided by 100 squared, and we get 0.01 meters squared. Okay, let's say the distance is a millimeter, which is reasonably small, but it's, as you'll see, it's not super small. That's 1.0 times 10 to the minus 3 meters. Oh, yes, that's right, because you move this 3 per 1,000 millimeters per meter. And we already have epsilon 0. I wrote that down. Epsilon 0 is 8.85 times 10 to the minus 12. Okay, so the capacitance of a capacitor that's 10 centimeters is about 4 inches, something like that, 4 by 4 with a millimeter between them. And so you get 8.85 times 10 to the minus 12th times the area, which is equal to 0.01 meters squared divided by the distance, which is 1.0 times 10 to the minus 3 meters. And the capacitance I get is 8.85 10 to the minus 12th times 0.01 divided by 0.001 basically, and you get 8.85 times 10 to the minus 11th, and the units for capacitance are farads. 10 to the minus 12th is pico, so it's 88.5 picofarads. So it's pretty small value capacitance given the fact we have a capacitor that's 4 by 4 inches and 1 millimeter apart. So we're going to have to do something else to improve the capacitance of a capacitor that beyond just making the area huge, because this is a reasonably big area. To make it, say, microfarads, you'd have to increase the area by probably 1 million or something like that. Okay, this video is about capacitors, both in parallel and in series. So let's just review what a capacitor does. A capacitor consists of 2 plates, and they're conducting plates, and they're connected through a number of different configurations possible, but the simplest possible configuration is to have a battery, which we'll say has 9 volts, and the positive side is here and the negative side is there. So when you connect the battery up to this circuit, the positive side will basically push positive charges to this plate and negative charges to the other plate. So in reality what happens is that the voltage creates an electric field in the wire which pulls electrons from the positive plate, from this upper plate. And that makes, when the electrons go into the wire, this plate becomes positively charged because it has more protons than electrons. Likewise, there's an electric field which pushes electrons into this side, and they don't come from the other side, they just come from the wire. So excess electrons are pushed here. So it's kind of like a domino thing. They just push each other out of the way and move the electrons in this direction. And what that does is it creates an electric field between the plates. So you have the positively charged plate and you have the negatively charged plate. And so you have an electric field which goes between the two plates. And if the plates are closely spaced in the area, so the spacing to the area is small, then the electric field is constant inside the capacitor. And what we know is that the electric field is just going to be equal to the difference in voltage divided by the distance between the plates. So this is the spacing of the plates right there. Because electric field is voltage divided by delta V over delta X. And in our case, our delta V is the voltage that's applied across the plates, and the distance, delta X, is the distance between the two plates. And so that's why the electric field is as such. And the ability for this particular electrical component to store charge, basically to move negative charge over here and remove negative charge from this side, is called the capacitance. So the capacitance of a capacitor is just the ratio of the amount of charge that can be stored divided by the voltage. So if you have a large capacitor, then for a given voltage, you're going to be able to store a lot of charge. And usually capacitances are, the units for capacitance are called farads. So this has units, charge has units of coulombs, and voltage, of course, has units of volts. So coulombs for volt, and we call that a farad. So 1 coulomb per volt is called a farad. Most capacitors are on the order of micro 10 to the minus 6. They're very small as far as the values are concerned. 1 farad is a huge capacitance. Okay, so now what happens, this is what we're talking about here, is parallel versus serial. So if this is a serial arrangement of capacitors. It just means they're connected end to end. And normally you would then put a battery, apply this voltage across all 3 capacitors. So again, this is the positive pole, this is the negative pole, we'll call this 9 volts. If all these capacitors were the same, what you'd end up with is 9 volts here, 6 volts there, 6 volts there, 3 volts there, 3 volts there, 0 volts there, and then you would go from 0 to 9 across the battery if they were all the same, just because from symmetry you can kind of think about that. So what happens is all the voltages are broken up into lesser amounts, so the sum of the voltages across the capacitors is going to be the total voltage that's applied to the capacitors. So this is what's called series. Then you have the other case of parallel. So let me just draw that. So we have a battery that's going to charge the capacitors, and you go over here and you have them like this. This is the parallel case. In this case, this 9 volts, the battery is going to be applied across each capacitor. So you'll have 9 volts here and 0 volts there, 9 volts there and 0 volts there, 9 volts there and 0 volts there. So each capacitor has the same voltage applied to it. And so it's going to get the full effect of that voltage in terms of charging the capacitor. So how does this work? Well, for this series case, the total voltage drop across the capacitors is going to be the sum of the voltages for each one of the capacitors. So let's call this voltage. We're really talking about change in voltage. So this is V1, V2, V3. They have capacitance C1, C2, C3. So the total voltage that's applied is going to be equal to the sum of the voltages. What happens is that this plate becomes positively charged. This plate becomes negatively charged. To get the electrons, they take them from the plate that's to the right. So the electrons from here push into the wire, and the ones in the wire are pushed out onto the plate. Likewise here, the same thing happens. You got electrons on the other side. You have the lack of electrons here, and they just moved. So they can't cross because you see there's not a complete circuit. Current never goes, electrons never cross this boundary because it's a gap. So all we can do is move electrons around within the system. So what we see is that the charge here, these have to match up. So the number of electrons that are here have to be balanced by the number of atoms that don't have electrons there. So the charge is going to be the same between them all. So for series, Q1 is equal to Q2 is equal to Q3. Just because we're just moving these within these little segments. Okay, so we can just call that Q. And so what we'll do is there's also the capacitance of each element. C1 is going to be equal to Q1 over V1. C2 is equal to Q2 over V2. C3 is equal to Q3 over V3. So if you solve for the voltage is equal to Q1 over C1. V2 is equal to Q2 over C2, and V3 is equal to Q3 over C3. So if we plug those in here, and so we're going to plug those in here, but what we're trying to do is we're trying to replace these three capacitors with an equivalent capacitance that behaves exactly the same in the circuit. So what we're having is, and the capacitance of the three individually is always greater than the equivalent capacitance. Okay, so what does that mean? Let's just stick that in there. So we're going to say that, so our total voltage is going to be basically our charge, which in this case is the same for all of them, divided by the equivalent capacitance. So if we plug those in, this is V total. So we get Q over the equivalent capacitance of the three together, and you just add these all together. You just plug them into the original expression for the sum of the voltages. So you get Q1 over C1 plus Q2 over C2 plus Q3 over C3. But remember, all the charges are the same because of the fact that we can't have any current flowing through here. So those all cancel out, and you get, for series capacitors, you get this relationship, that the equivalent capacitance of, in this case, three capacitors in a row is the same as replacing it with one capacitance that is derived from this expression. Okay, so that's for series. For parallel, it should be parallel, not parallel. So the key thing over here was this: the charge in each capacitor is the same. For parallel, V total, which is 9 volts in the case that we're looking at, is the same for all three capacitors. So what we can say is that also that the total amount of charge that's going to be stored on these capacitors is going to be this plus that plus that. Because there's nothing saying that we can't have a different amount of charge on this plate than this plate, and a different amount of charge on this plate. The only reason they were the same here is because they were connected. Here they're not connected. They're connected in that they have a common voltage, but they're not limited to the same charge on each capacitor. So we can say that the total charge on all three capacitors is the sum of the charges individually. So we do the same thing, is that we're going to be able to cancel this out, the voltage, because it's the same for everything. And we're going to again use the definition of capacitance, but we're going to solve for Q. So if we take that, we get Q1 is equal to C1V1, Q2 is equal to C2V2, Q3 is equal to C3V3. Each V1, V2, and V3 are all 9 volts in our particular example. So we can make these substitutions. So we can say Q total, which would be C equivalent times the voltage total, is equal to Q1, which is C1V1, Q2, which is C2V2. That's the charge, and the product of these two is the charge in each capacitor. But because Vt is equal to V1 is equal to V2 is equal to V3, they all cancel out. And so for capacitors in series, you just add the capacitance values. So let's just look at an example, 2 cases. So let's look at the series example, and we'll just pick 3, and we're going to pick them so they're easy to calculate. So if I wanted to replace these 3 capacitors, which are in series, with an equivalent capacitance, and let's say this one is 1 farad, this one's 2 farads, and this is 3 farads. Okay. Normally we don't have that many capacitors, but just for the ease of math, all we have to do is we say for series capacitances, we use this relationship right down here, the bottom left hand. So we can say 1 over the equivalent capacitance of the series is 1 over C1, which is 1 farad, plus 1 over C2, which is 2 farads, plus 1 over C3, which is 3 farads. Okay, so what we have is 1 plus 1/2 plus 1/3. So you'd find a common denominator. So you'd have 6 over 6. I'm going to drop the f's for right now just so it's easier to deal with. 1/2 is the same as 3/6. 1/3 is the same as 2/6. And that's equal to 1 over the equivalent capacitance. So we add those. 6 plus 3 is 9 plus 2 is 11. So we get 11/6 is equal to 1 over the equivalent capacitance. And therefore, because these are just 2 ratios, you just have to change the numerator and the denominator. And you get the equivalent capacitance is 6/11 farads. Notice that this 6/11 is less than any one of the original capacitances. So putting capacitors in series results in a lower equivalent capacitance. Now, the second case is where you have these in parallel. So we've got this, and these again have the same voltage applied to them, because the top terminals have the same, are connected by the same wire. We assume there's no voltage drop across the wire. So this will say is 1 farad, this is 2 farads, and this is 3 farads. And so what is the equivalent capacitance? Well, in this case, it's very easy. You just add them together. It's just C1 plus C2 plus C3. We'll call this one C1, this C2, and this C3. So you just add them together. So you get 1 farad plus 2 farads plus 3 farads, which is equal to 6 farads. So the equivalent capacitance is 6 farads. So you could replace this like in the previous example, we could replace those 3 with one capacitor that has a value of 6/11 farads. That would be the equivalent capacitance. Over here you can do the same thing. We can place those 3 capacitors in parallel with one capacitor in parallel, which is going to have a value of 6 farads. And these are going to behave exactly the same. These 3 are going to behave exactly the same as the 1, or the 1 is going to behave exactly as 3. So it's saying you can store. So if you want to store a lot of energy in a set of capacitors, you want to hook them up in parallel. You don't want to hook them in series. That's not going to work. Again, it's because each of them have the same voltage across it. The voltage is what governs how many electrons are put on.
This is going to be an example of how you do the calculation of a little more complicated arrangement combinations of series and parallel capacitors. And then we're going to figure out how to calculate the voltages across each one of the capacitors. So let's I'm going to go ahead and put a battery in here. So let's say we have a circuit and that breaks up into 3 capacitors like this. Actually, in this case, I'm going to add another one here. So then these all will meet. And then we'll come down here and we'll have some capacitors in series, additional capacitors in series. Okay, so we got two in series, then we got these 2 in parallel with those 2. And let's give them some numbers. And again, I'm going to just do them in farads. Well, let's put them in microfarads, but what we'll do is we'll just drop the micro part until we get to the end, just to make it easier. So let's say this is 1 microfarad. This is 2 microfarads. This is 4 microfarads. This one is 0.5 microfarads. This one is 3 microfarads, and this one is 2 microfarads. The question is, how can I rewrite this as just one capacitor? So what you basically do is try to look at the innermost part, which is this one right here. What I'm going to, here's the strategy is I'm going to change these 2 into a single capacitor. Then I'll have 3 single capacitors in parallel. I'll combine those into 1 capacitor, and then I'll have left over, I'll have this equivalent capacitance, and then these 2, which will give me 3 capacitances in series, and I can do it as in series. So it's kind of, let me just draw this, what it looks like. So the first case is I don't do anything with the top 2, but the bottom one I'm going to combine. The bottom 2 in that sequence is I'm going to combine this into 1. Okay, and then this comes out over there. And then we've got these 2 right like that. Okay, so that's the first step. Combine those 2. The second step is I'm going to combine those 3. So we'll then use capacitors in parallel. So I'll replace those 3 in parallel with 1 capacitor. That'll bring me down to here. And then I'll have 3 capacitors in series, and then I'll only have 1 left. After I do that, I'll just combine these 3 with 1 capacitor. And there you go. So that's how it works. You just have to use the rules for each one of these steps. So what we need to do first here is to find out what that is. So I'm going to do this over here. So capacitors in series are resistors, which we'll talk about later, are exactly opposite of the capacitors. So resistors you add together. Here you have to use this expression. So the two that are in series, you use the inverse relationship. And I'm going to just leave off the microfarads until I get to the end. So we're just going to put them in as 1 and as 2. So this is 1 and 2. And so what you get, 1 plus 1 and 1 plus a half is going to be 3 halves. You take the reciprocal, you get 2/3 microfarads. Okay, added the micro there. Okay, so that's what this is going to be. So I can put in here, let me put in 0.667 microfarads. The middle one here is 4 microfarads. This one is 0.5 microfarads. This one is 2 microfarads. This one is 3 microfarads. Okay, so now what we're going to do is we're going to combine these 3 into this one. So because they're in parallel, all we have to do is add them together. So we have 0.5 plus 4 plus 0.667. And so the equivalent capacitances of those 3 will be 5.333, I think. 4 plus 0.5 plus 0.6666666. Oh, 5.16. Glad I checked it. Okay. Microfarads. So we can then make this into 5.166 microfarads. This one is still 3 microfarads. This one is 2 microfarads. Okay, let me just add a page. So here we have 3 in series, so we have to use the series expression. So we get 1 over the equivalent capacitance is 1 over 5.166 plus 1 over 3 plus 1 over 2, and it might be easier just since we've got decimal points in there just to do them in the calculator. 1 divided by 5.16666 plus 1 divided by 3 plus 1 divided by 2 is 1.0268. Okay, so we get 1.0269, rounds off. And if you take the reciprocal of both of those, you get the equivalent capacitance is 1 over that, which is 0.973 microfarads. This should be less than each one of these individually, and it is. So we're looking at the numerators here, denominators. So is this less than either of all those 3? Yes, it is, so at least that's correct. So if you go over here to the left, the equivalent single capacitance value, which is the same as the original combination of 1, 2, 3, 4, 5, 6 capacitors, is 0.73 microfarads. Okay, so now how do we figure out the voltages are? How are the voltages separated? So I'm going to add a page here, and you kind of work backwards once you know that. So we know that across a single equivalent capacitance here, the final, that's 9 volts, because we have the voltage goes from minus to plus here, it goes from plus to minus there. And so that, now the question is how does this get separated? So what you do is you just look at each one of these, and I'll do it in a different color, blue, and we'll call this A, B, and C. So you use the definition of capacitance. So capacitance of A is voltage across A divided by, the charge, Q, divided by the voltage across A. Now, the Q actually you get from down in the previous step. So what is the charge on this capacitor, the equivalent capacitor? Let's just do it over here. So that was the equivalent capacitance. The voltage is equal to 9 volts. So we know that capacitance is equal to Q over V. Therefore, Q is equal to C times V. And so Q is equal to the equivalent capacitance, 0.973 microfarads times the voltage, which is 9 volts. So we get 0.973 e to the minus 6 times 9. So the total amount of charge across the equivalent, the last equivalent capacitance is 8.757 times 10 to the minus 6 coulombs. Okay, let's write that in. So the charge here is 8.757 times 10 to the minus 6 coulombs. And what's going to happen is, going backwards, this charge across the equivalent capacitance is the same across each one of these. So what we can say coming up here is that for this part, for the part that we go back one step, Q is equal to 8.757 times 10 to the minus 6 coulombs for every one of these capacitors. So the numerator stays the same. The only thing that changes is what's going to change is the voltage. So we're going to solve for the voltage. I'll give you the charge divided by the capacitance. And we do this for each one of these. So the voltage across the capacitor A is the charge, which is equally distributed to each one of the capacitors, divided by the capacitance of each element. So we take that, we divide by 5.1666666 e to the minus 6. We get 1.694 volts. So that's the voltage drop across this capacitor. When we do all three of them, when we add the voltages up, they should come out to be 9 volts because the total voltage drop has to be that. So all we do is keep the same charge for each one of those capacitors. Change the capacitance. This next one is 3 times 10 to the minus 6 farads. 8.757 divided by 3. And I'll get 2.919 volts. That's for the capacitor B, and for capacitor C, same charge. Different capacitance. Notice they both have 10 to the minus 6, so I can just add this by that. The 10 to the 6s will cancel out. So they get 8.757 divided by 2 is 4.379. And if I add all those up, it's going to be very close to 9 volts. It's just the question is in terms of rounding off. So if I'm adding those three together, and I get 9.02, so I get a little bit of error in my rounding off. But you can see it's pretty much 9 volts. So you have 1.694 across this capacitor, 2.919 across this capacitor, 4.399 across this. They all add up to 9 because when you come back here, the increase in voltage across the battery has to equal the sum of the voltage decreases across there. Okay, so what do we do next? Now, we go to this step. So we're going to have this capacitance broken up into 3 parts. The key thing is that I have the charge, 8.757 times 10 minus 6, and that charge has to be separated amongst these 3 depending upon their magnitude. So what we can say is that Q total, we're just talking about this part, is equal to, and let's use some different numbers here. Let's call this E, F, and G. So we can say the total charge across those 3 capacitors has to be the sum of each one of them. So the charge that is on this equivalent capacitance we know what that is. That's 8.757 times 10 to the minus 6 coulombs. And so this has to be broken up accordingly. So how does that work? Well, what we're going to do is, well, the other thing we know is the voltage drop across each of these is going to be equal to, we calculated it here just a minute ago. So A is this equivalent capacitance. So that's going to go back with the same voltage. So we can say that the voltage drop across each one of those individual capacitors is the same. So when you go from here to here, this voltage drop is the same as the voltage drop across the whole thing. So that is the key. We can then calculate the capacitances for each one of those. We can calculate the charge on each one of these capacitors, again, using the definition of capacitance. Capacitance is charge divided by voltage. What we're trying to find is Q. Q is equal to capacitance times voltage. So, and it's going to work out. We're going to use this to check our results, but we don't need that. We don't need that number. It's going to fall out automatically. So what we can say is that the charge on element E, which is this one, is just equal to its capacitance, 0.666 microfarads times the voltage, which is not 9 volts, but 1.694 volts. And Q for capacitor F is equal to 4 microfarads times 1.694 volts. And QG is 0.5 microfarads times 1.694 volts. So we can do all those calculations. And when we do that and we add them up, we'll end up with 8.757 as a check. So 0.6666 times 1.694, I get 1.129 times 10 to the minus 6. And charge is coulombs. 4 times 1.694 is 6.776 times 10 to the minus 6 coulombs, and 0.5 times 1.694 is 0.847 times 10 to the minus 6 coulombs. And if you add all those up, 1.129 plus 6.776 plus 0.847, it should equal 8.757, and I get 8.752. So it's, again, just an artifact of rounding off. So the total capacitance, total charge across this has to be the same as the sum of the charges of the 3 individual ones. So that gives me the charges for each one of those. We know the voltage, we know the capacitance, we know the charge, so we know everything now. So the last part is we're going to go back, we're going to take this part, and we're going to say, now we know the voltage, and we're just going to break that up. So we're going to look at this one. So what we're going to do is go, let me add a page here. So what do we know at this point? We have the total voltage across here. If we go back, it's, where's the voltage? 1.694. Okay, so the voltage across here is 1.694 volts. And we know that the charge across here, bring it over there, is the charge that was associated with this. So the charge for that part, that was E, is 1.129 times 10 to the minus 6. 1.129 times 10 to the minus 6 coulombs. So what we're asked for, we know that the charge on this plate is 1.129 times 10 to the minus 6. The charge on this plate is 1.129 times 10 to the minus 6. This will be positive, this will be negative, this will be negative, this will be positive. So we have the same charge on each one of these plates. The question is, what is the voltage between these two? So what we have to do is we have to, again, use the definition of capacitance, which is Q over V. And what we're trying to figure out is, what is V? V is equal to Q over C. If I just switch these, I've got a ratio. So I can move that down there and move that up there. So the voltage across each one of these capacitors is going to be based on the charge, which is fixed, divided by the individual capacitance. So let's call this, we said G, H, I, J. Let's call this J, and this K. So what we can say is the voltage across capacitor J is equal to the charge divided by the capacitance. The charge is this 1.129 times 10 to the minus 6 coulombs. The capacitance is, for J, it is 1 times 10 to the minus 6 farads. 1 divided by 1.129, so you get 1.129 volts. So that's the voltage across capacitor J. And then the voltage across capacitor K is, again, Q over C. This is C sub J, this is C sub K. Q is the same. So you get 1.129 times 10 to the minus 6 coulombs divided by 2 microfarads. 2 times 10 to the minus 6 farads. So we get 1.129 divided by 2. You get 0.565 volts. And if we add these two voltages together, we should get 1.169. So 1.129 volts plus 0.565 volts. 1.129 plus 0.565 is 1.694. 1.694 volts, which is the same as we got here. Okay. So that's the way it works. I know it's a little complicated, and you have to just kind of get used to doing it, going back, forwards, and backwards. So you can watch it again if you're interested. Okay, we talked about capacitors. Capacitors are electrical elements that store energy through a magnetic field, through an electric field, pardon me. And we have 2 plates that are parallel to each other. So we have one plate and another plate. And so one side becomes positively charged and the other side becomes negatively charged somehow or another. Typically, you have a circuit which applies a potential voltage which forces the electrons out of this plate and into the other plate. And we came up with the calculation that the capacitance was equal to epsilon 0 times the area divided by the distance between the plates. So these are the area of the plates, this is the distance between the plates. This is a constant that's related to Coulomb's constant. And if we calculate capacitance for normal capacitors based on this, we would get really small values. Well, it turns out that if you put a material between the plates that has certain properties, which we call a dielectric, and it's spelled right? No, dielectric, sorry. It's DI. So here's what happens. These are typically molecules that have some polar nature to them. And so before the potential is applied to this, you have these kind of randomly oriented, where they have a plus side and minus side. But they're all, since they're so randomly oriented, they kind of cancel each other out. So I'm just showing some random ones that look like kind of little single-cell organisms, but they're not. So this is before we apply a voltage and get these to happen. So now what happens is you apply voltage and you get these charges on the different plates. You get positive charge over here, negative charge over there, and that creates an electric field. Now, because these little blobs here, these materials, can align themselves, what will happen is they will align themselves. It actually goes the other way around. So the negative side attracts the positive side. And let's see if I can grab that. So this will switch around like that. No, I'll do the wrong way again. So this will actually go around to there. And then this one will align, both of those. Anyway, what happens is that these align, and as a consequence, they create an electric field because of these aligned charges that go opposite the direction of the originally applied electric field. So you got these superimposed. You got an electric field that's due to this charge difference on the plates, and then you have this electric field in opposition. So we can kind of say what happens is the electric field, the net electric field, is the sum of these two. So there's, I guess you'd have the electric field imposed by the charges, and then you're going to subtract the electric field that's induced by the alignment of these molecules within the dielectric. And what that gives you is this net electric field is less than the originally imposed electric field. And because of that, what that allows us to do is then what's limiting how much charge can be on these plates is the electric field between these two. So since the net electric field is less now, we can put more charge on each plate. And so we store more energy for a given voltage that's applied. So if we remember the definition of capacitance, it's charge per unit per voltage. So since we're able to put more charge on the plates for a given voltage, the effective capacitance of the capacitor goes up when you put a dielectric material in there. So how do we do this numerically? Well, you can say that the capacitance of the capacitor is equal to some constant K, or kappa, times C0, where C0 is the 1. 0 stands for a vacuum, and that's what we had calculated previously. So you have this dielectric constant, that's what it's called, dielectric constant, K, or kappa, that is a function of the material that you put between these two, and it gives you an effective capacitance higher than the one that you would calculate just from having a vacuum between the two. So you can also say that the capacitance is equal to kappa, the dielectric constant, times epsilon 0 times A over D. It's the same basic thing. So if I substitute that into here, I get that. So what are some typical dielectric constants for materials? Well, air is pretty much close to 1. And if you look in the book on page 558, table 16.1, you'll see this neoprene rubber. That's the kind of rubber that you use for like sleeves for supporting joints. it has a kappa equal to 6.7. So if you were to substitute, if you were to slide this in between this rubber, you'd be able to get 6.9 times the amount of charge per given voltage. And then you've got things like strontium titanate, whatever the heck that is, some chemical. And its kappa is equal to 233, so it's going to be 233 times as much charge. Water has a fairly high one because it's polar, so it has a kappa equal to 80. Now, typically you want this not to be water, but you want it to be something that's solid, because by having something in between the two plates, it'll also kind of electrically insulates the two sides. So if you had air, you might have a roughness in the surface and you couldn't guarantee that they didn't touch. Whereas if you take, two plates, again, two parallel plates, and you have some material that you can stick in between, whatever that is. Let's draw. So this is the material. Then I can guarantee that they're not going to touch because it's a solid. I put that right up against the red thing, and I put that right up against the red thing. So not only does this material inside increase the capacitance because of the dielectric constant, but allows me to make D very thin, small. So it's kind of like a spacer as well. And as long as the voltage across the capacitor is not too large, then this barrier will prove effective. Now, if you put too high voltage, then it's going to arc through the material and it'll destroy the capacitor. So that's what the dielectric material does. It increases the capacitance by taking these polar molecules and aligning them according to the negative side going towards the electric field, and the positive one's going kind of like downstream. It's almost like something in a river. If you have your canoe aligned with the river, it's going to go much smoother.